Okay, perfect. Thank you very much for inviting me to talk, and I apologize that I'm not able to attend in person. I've just came back yesterday from Canada, actually, and going all the way to the other side of the world would have been too much travel. Slide 2, please. A very brief motivation of why one wants to do numerical relativity. There's a few different primarily reasons to do so. To learn more about astrophysics, what happens when stars collapse or compact objects collide. To elucidate properties of general relativity related to gravitational waves or not. For instance, the image on this slide is about critical collapse to black holes and criticality in black hole formation. But most important presently is to aid gravitational wave detectors, today ground-based detectors, but in the near future, hopefully space-based detectors and also pulsar timing arrays. Slide 3, please. LIGO and other ground-based gravitational wave detectors rely on input from numerical simulations on a broad array of different tasks. The most immediate one is to detect signals, where LIGO uses template banks for matched filtering, and where also numerical simulations are used to inform the data analysis routines of the shapes for actual signals in order to reject instrumental artifacts to veto systems. Detection efficiency relies on injecting waveforms for those systems that are not being searched for, but for which one nonetheless would like to get a bound on how well the instruments can detect them. Searches are for aligned spins, and so for detection efficiencies, one would inject processing systems or eccentric systems, run recovery, and that way quantify sensitivity. Parameter estimation, next, very roughly speaking, works by comparing possible signals, possible waveforms, with the actual data observed by LIGO. And in order to make such type of comparisons, you need to know the waveforms for all parameters that you want to estimate, the masses, the spins, sky location, eccentricity, and so forth. And once neutron stars are going to be seen in LIGO sources, electromagnetic properties and neutrino counterparts will also become very important to inform telescopes what to look for and to interpret any electromagnetic counterpart that may have been observed. As you can see, besides electromagnetic counterparts, the primary input of numerical simulations are the waveforms. Slide 4, please. A brief reminder of the systems we're actually looking at. I will be focusing henceforth on binary black holes. So black holes have about 100 to 200 kilometers diameter, and they're separated by about 1,000 kilometers. So southern India fits nicely. And the basic properties of the system is just mind-boggling. Velocities of near the speed of light, gravitational wave emissions of several solar masses and energy within a second, about 10 to the 20, 10 to the 21 times the solar luminosity. Slide 5 puts the numerical simulations in context to the previous and the next talk. Typically, the earlier part of the Inspiral for compact object binaries is simulated with post-Newtonian methods, like the ones Guillaume just introduced. Numerical relativity then can be used to model the late Inspiral merger and ringdown of the system. And in order to get complete waveform models, one typically has to connect analytical models early on with numerical data for merger and ringdown, and that will be the topic of Frank's talk immediately after mine. Slide 6 Another view of the different approximation schemes for compact object binaries. Post-Newtonian theory is good at large separation of the binaries. Numerical relativity is good at small separation and at comparable masses, mass ratios 1 to 20 roughly these days. And at higher mass ratios, one could do perturbation theory in the mass ratio and cell force calculations. But again, that would be topics for a different talk. Let me now get into more details of numerical relativity with slide 7. The basic ideas of solving Einstein's equations is actually quite straightforward. The goal is to find a space-time metric that satisfies Einstein's equations, RAB of GAB equals 0. And the first step towards doing that is to split space-time back into space and time by introducing an explicit time coordinate t and considering hypersurfaces labeled by different values of time. Doing so, Einstein's equations split into evolution equations that give the time derivatives of certain quantities and into constraints that restrict those quantities labeled g and k on my slides within each hypersurface. So this overall structure is similar to Maxwell's equations, where you have the curl equations that tell you how the E and the B field evolves forward in time. And you have the divergence equations that restrict the possible choices for E and B at each instant in time. And I've written them down here for vacuum without any charges. So basic picture is quite straightforward to explain. Slide 8 lists a few of the difficulties why numerical relativity is a difficult problem. There are singularities inside the black holes, which one has to deal with and get the computers to solve. The constraints, the equivalence of the divergence equations of E and M, turned out to be quite difficult to preserve in an evolution. And for many decades, constraints would be increasing extremely rapidly during a numerical evolution, rendering the system physically meaningless way too quickly. Coordinate choices are also interesting and difficult because one needs to choose coordinates for a space-time one is just about to solve and then one doesn't know yet. For comparable mass black holes, coordinate choices seem to be well under control, but as you go to large mass ratios, 10, 20 and above, again, coordinate choices become an active research area. And numerics is difficult, about 50 variables, tens of thousands of floating point operations per grid point, different length scales, small black holes, from small black holes to large wavelengths of the gravitational waves, and quite high accuracy requirements for gravitational wave modeling. Slide 9 gives a very dense history of numerical relativity. I won't have any time to go into any details, but roughly there are two phases on this plot. Before 2005, a lot of foundations were laid to figure out how one of all the different ingredients that are needed for black hole simulations. Then 2005, 2006, in the red boxes are the key breakthrough results. Pretorius doing harmonic simulations, University of Texas Brownsville, now RIT and NASA developing in the BSSN simulations, and then SXX, Cornell, Caltech, somewhat later the Spectral simulations. And those breakthrough simulations, those breakthrough results have then changed the character of the field from mostly algorithmic development to scientific and physics applications henceforth. Slide 10 There's currently two major approaches in use worldwide to simulate black holes. One goes under the name of BSSN, the other one goes under the name of generalized harmonic. And they differ in virtually all respects of the formalism and implementation. First of all, towards the top of the slide, the two approaches use different types of initial data. The BSSN evolution, shown on the left-hand side, typically use puncture initial data that goes from one asymptotically flat end through Einstein-Rosen bridges to the other asymptotically flat end. Whereas the harmonic approach uses quasi-equilibrium excision data that starts at an asymptotically flat end and only solves initial data up to the horizon or slightly inside the horizon. The BSSN evolution system is reasonably close to the ADM equations I've spelled out earlier, essentially evolving 3+1 split quantities for the Einstein fields, whereas the generalized harmonic system evolves the space-time metric itself. Finally, not necessary, but just happened the way history worked, the BSSN evolution codes and the harmonic evolution codes also use different numerical techniques to evolve the various sets of equations. BSSN tends to use finite difference evolution schemes with adaptive mesh refinement, usually based on cactus and carbid. The generalized harmonic camp, mostly represented by the spec code and the SXX collaboration, uses multi-domain spectral methods, about which I will say a little bit more in the following slides. So, as one example of an evolution code, I'd like to introduce for a few slides the spec code. Slide 11 spells out the name Spectral Einstein code and gives the main collaborators of our collaboration: Caltech, Cornell, CETA, AEI, Fullerton University, and Washington State University. Slide 12, spectral methods expand solutions in basis functions. For instance, a function u of x and t would be represented as a sum of spatial basis functions phi k of x multiplied by time-dependent coefficients u tilde of t. And the goal now essentially is to evolve or solve for these spectral expansion coefficients u tilde. The nice thing that this type of expansion gives you is that quite a lot of aspects of the problem can now be solved exactly. For instance, derivatives can be computed analytically because we know the derivative of the basis functions. The basis functions might be Chebyshev polynomials or spherical harmonics. Other aspects are not quite as easy. Nonlinearities are really computed in physical space. So it goes back to a physical grid and evaluates any nonlinear terms there on the physical grid before then transforming back into the spectral representation. Slide 13, we use black hole excision, where we take advantage of the light cones tipping over inside the event horizons. And so we can place the red artificial boundary inside the horizons of the black holes. And because the light cones have completely tipped over and all information propagation is into the interior of the black hole, and because the generalized harmonic system has only physical characteristic speeds, at most the speed of light, even all the gauge fields, the coordinate degrees of freedom, move at best with the speed of light. Therefore, at such an artificial boundary, we do not need to impose any boundary conditions at all. Slide 14 gives a nice show-off picture of the domain decomposition near the black holes, which aren't visible on this plot because they're too small. we use first spherical shells, indicated here in cyan and dark blue. At intermediate distance around the spherical shells, we place various cylinders or distorted cubes, indicated in green. And at large distance, indicated in orange, this is another set of concentric spherical shells. Each one of these subdomains has their own set of basis functions and their own expansion coefficients. The type of basis functions differs. In spheres, it's spherical harmonics. In cubes, it's Chebyshev polynomials. And this quite complicated Zellning schemes allows us to excise singularities. It allows to adaptively change resolution. We have AMR implemented by changing the number of basis functions separately in each domain. And we can also parallelize by putting different subdomains on different CPUs. Slide 15 gives some context for what's going on near mergers, where the black hole horizons have been strongly deformed. We are deforming the computational grid to follow the horizons of the black holes, and that can lead to quite deformed grids like the one shown in the top right panel. Once the black hole have merged and we have detected a common apparent horizon, we switch to a different domain decomposition that only has a set of concentric spherical shells extending from just inside the common apparent horizon and out to very large outer radius. Okay, let me now switch over and discuss a few applications of numerical relativity and give you some context of how much the field has improved over the last years. Starting with slide 17, I'd just like to point out one illustration of improvement is the length of the simulation, where Pretorius in 2005 only simulated the merger with very little end spiral, and the Goddard group and other groups very quickly thereafter, RIT as well, pushed this up to about 5 orbits very quickly. And very early on it became clear that numerical relativity or binary black hole waveforms look quite simple and show very continuous transition from Inspiral to Ringdown without a lot of extra features near merger. And so that basically showed that it's possible to do waveform modeling for binary black holes. Slide 18 illustrates how equal mass simulations have continued since. With the Spectral Einstein code, we were able to push length quite impressively, going to 15 orbits and 13 orbits in the top right panel. And then more recently, led by Bela Szilágyi at Caltech, we were able to do a simulation lasting 170 orbits, shown in blue in the lower panel. Another illustration for the improvement of simulations is on slide 19, an impression of the number of simulations over the last years. And in 2009, the first Ninja project, the left-hand side plot on slide 19, shows all the waveforms that were available in 2009 worldwide. Just a few years later, just one of the collaborations doing numerical relativity work, the SXX collaboration, was able to compute catalogs with about 200 waveforms, each one much longer than the original Ninja waveforms. And on slide 20, as of early 2016, there's now worldwide in excess of 1,000 simulations that have been performed by quite a few different groups, going alphabetically. The BAM code, primarily run these days by Cardiff and Palmer, focuses on waveform modeling. Georgia Tech focuses on merger waveforms and ringdown properties of the waveforms, how ringdown modes are coupling to the and still convey information about the individual black holes that have been merging. RIT, Rochester Institute for Technology, has put a lot of effort into formulas and quantifying remnant mass spin kicks. And my collaboration, the SXX collaboration, our focus has been on waveform modeling, in particular with very long inspirals. And just one of many illustrations I could put up here for the many simulations that are being done. The plot on page 20 shows the reduced order waveform model developed by Jonathan Blackman at Caltech. And it shows the parameters of about 200 new numerical relativity simulations done for this, covering spins between 0 and 0.8. And in this particular case, covering mass ratios only between 1 and 2, because this model is geared towards the first gravitational wave event. Slide 21 gives a little bit more impact for why one wants to do these particularly long simulations with the 170 orbits. As you can see in the top right panel, that contrasts a more typical 20-orbit waveform in yellowish orange with the 170-orbit waveform. What you're gaining with the extra cycles is much better reach towards lower frequencies, cutting the initial frequency by roughly a factor of 3. And so actually for reasonably large masses, we're now able to cover with some of these simulations the entire advanced LIGO noise curve and perform tests like the ones shown on page 22, where we can quantify how good or bad different waveform models are in this earlier part of the waveform that previously was only accessible with post-Newtonian techniques. And so, as we've shown in a study about a year ago, the earlier phenomenological waveform models and the plain old Taylor post-Newtonian models give quite large errors, whereas the EOB waveform models that Guillaume was already mentioning earlier are remarkably accurate. Switching over to aligned spin waveform modeling, I'm showing here the parameter space of the numerical relativity waveforms that were used for modeling for two of the important EOB and R waveform models. And as you can see that the V2 has much bigger support in terms of numerical relativity, but there's still only very few simulations that have spin in them that were used for fitting those waveform models. And those typically, most of them only have spin on the bigger black hole. And even there, most of the spins are typically only plus minus 0.5 or 0.6 or thereabouts. Nevertheless, the waveform models are used pretty much everywhere in parameter space, up to spins of 0.98 or 0.99. And so there's a large extrapolation going on, which needs to be quantified whether this actually has impact on the waveform models. Switching to slide 25, I'll skip 24. I'm showing a few of the new simulation we've done to test those waveform models. And so the new thing with this set of simulations performed by Tony Chu is that we actually attempted to cover most of the spin-spin plane up to spins of 0.9 on both the big and the little black hole, aligned and anti-aligned. And with this quite large new set of simulations that's shown as the blue circles on the right-hand panel of slide 25, we can now actually go on and test the existing waveform models and subsequently construct better ones. Slide 26, just to show off, are all the 90 or so new waveforms we have computed in this particular project. Slide 27 is an analysis of the waveform errors. And on the x-axis here is the error of each of the simulations in terms of mismatch, noise weighted by the advanced LIGO design sensitivity. And essentially all simulations have mismatches errors less than 10 to the minus 3 and many of 10 to the minus 4. What actually surprised us quite a bit when doing this analysis is that the techniques being used to extract the gravitational waveform leads to the dominant source of error. In this particular project, for the first time, we did a very large-scale comparison between two completely different ways of extracting gravitational waves, Ricci-Villa-Cerilli extraction and Cauchy characteristic extraction. Essentially, every other numerical relativity simulation and waveform being used only does Ricci-Villa-Cerilli extraction. But doing both here, we could actually compare the two techniques with each other and found that the uncertainty in the waveform extraction is the dominant source of errors for these calculations. Slide 28 shows one of the analyses we've done. We basically confirmed that recent waveform models, SUB and RV2, as well as the IMR phenom D model, are absolutely good enough to do gravitational wave searches in the region of parameter space where gravitational waves so far actually have been found. Because of lack of time, I will be switching forward quite significantly to slide 35. I'd like to highlight some pieces of work not done by the SXX collaboration, but by others. And one very important aspect are the connections between the individual binary black holes, M1, M2, and spins, to ring-down properties like masses and spins and black hole kicks. Slide 36 shows black hole kicks. Those were developed in the early on when numerical relativity simulations worked. Slide 37, a result I find more exciting because it offers so many exciting tests in the future, I think, shows a plot that shows the ring-down amplitudes as a function of individual black hole spin. And many of the modes are insensitive to the quantity plotted on the x-axis here, which is a certain summary of the inspiral black hole spins. However, one of the modes shown in red here has a quite sensitive amplitude to the initial data parameters. And so if this 2-1 mode could be observed in the ringdown, it would give yet another way of breaking degeneracies of the binary black hole waveforms that occur in that LIGO can observe. Of course, also somewhat more pedestrian, ringdowns and ringdown modes provide a very good test of general relativity, as I believe has been discussed in this conference already yesterday. Switching on to slide 39, I'd like to spend my last 2 or 3 minutes on summarizing the contributions numerical relativity made to the gravitational wave discovery of last year. Slide 40 shows the most visible contributions, and that were a large number of visuals for press conferences, talks, outreach. To go around the circle here, the top left panel shows Kip Thorne at the press conference, showing a movie that I made. The top right panel showing a German newspaper article with a waveform and a movie generated at the AI in Potsdam. Bottom left, the Lansing movie has been particularly popular. It was generated by folks at Cornell University. And the bottom right is a still image from also a very nice movie by Georgia Tech that's still gracing the LSE webpage. With remote talks, it's difficult to show movies, so on slide 41, I just list 2 URLs that have quite a few different movies. I encourage you to go there and watch some of them at your leisure. Turning over to the science impact that numerical relativity had on slide 42, again, quite significant. All the waveform models that were used to search for binary black holes and to do parameter estimation on them are based on numerical relativity input. The LSE made statements about the remnant mass and spin and the energy emitted in gravitational waves. All these quantities were computed by numerical simulations. And after the detection, starting in September last year, numerical relativity ran a significant number of targeted simulations near the parameters of the event to quantify systematics of all the LIGO flagship analysis, parameter estimation, burst searches, as well as testing general relativity. In fact, almost all tests of general relativity rely on numerical relativity because if you want to compare observations with the prediction of a theory, you need to know the predictions of that theory. And for the strong field nonlinear regime in numerical relativity, this can only be done with numerical simulations. Slide 43 shows 2 figures from the discovery paper, as well as the cover of the physical review letters. And with the blue arrows are information in these figures that directly come from numerical simulations. In those figures, the simulations being used were done independently by RIT and SXX, running simulations for identical parameters and actually cross-checking against each other that the numerical simulations are reliable and are correct. Let me summarize on slide 44. Numerical relativity for binary black holes has come remarkably far. It has contributed deeply and in an essential way to gravitational wave science and to GW150914. Long-term by constructing waveform models and improving waveform models, as well as scoping out remnant properties. And short-term to provide targeted systematic studies near the parameters of the system. As good as black hole simulations currently look, there's still a tremendous amount of further work that needs to be done in the coming years. Precession and higher order modes need to be worked out much more carefully than so far, because higher order modes provide one important potential route to break degeneracies in parameter estimation. GW150914 luckily was at very modest spins and very modest, almost equal masses, so that's a very easy case to do numerically. But pushing numerical simulations to more extreme mass ratios, especially mass ratio 5 to 10, is particularly relevant for black hole neutron star binaries. And spins beyond 0.9 are still a big challenge and active work. Eccentric binary black holes have received very scant attention so far, but if you want to measure eccentricity of any black hole observations, or also just to bound eccentricity based on observations, you need to know eccentric waveforms in order to know what you're looking at. Also, along the lines of testing GR, simulations of alternative theories of gravity will become more important. Again, in order to test how consistent putative alternative GR binary black hole waveforms would be with the observations of LIGO. What would be an entirely different talk, and at least as important as binary black holes, are meta systems, mixed binaries and binary neutron stars. Essentially because there's so much more physics going on, accretion disks, electromagnetic counterparts, prompt collapse to black holes or delayed collapse to black holes. And so again, a very active research area, which I simply didn't have time to cover in my talk. Thank you very much.
Okay, thanks, Harald. So, are there any questions for Harald? Yes, Ajit has a question.
Hi, Harald, this is Ajit. Hello? Hi, Harald, what are the prospects of, the near-term prospects of getting some numerical relativity simulations of alternative theories of gravity?
So the prospects are very low. Alternate theories of gravity basically fall into two categories according to my quite limited knowledge. On the one side, there are those theories that are easy to simulate numerically, but which are already excluded to a quite good degree with other tests of GR. Here, for instance, there would be scalar tensor theories and similar theories. Those can be simulated, but for instance, scalar tensor theories, black holes just look like GR black holes, so there wouldn't be a lot of different changes. On the other hand, there is radically different formulations of theories, like F and of R theories or Gauss-Bonnet gravity. In those theories, the principal parts of the evolution equations look significantly different from just general relativity. So simulating such theories require significant efforts in retooling the numerical relativity codes and adjusting them to those theories of gravity.
To expand the parameter space of the numerical relativity simulations, such as high mass ratios, do you anticipate some major breakthroughs, or are they required?
We can make, okay, so the difficulty with higher mass ratios and also very large spins is computational cost. The current computer codes just run very, very slowly. They do run, and we can do simulations that just take a very, very long time. But it would be useful to have breakthroughs to speed up those calculations. In the short term, I would expect we will continue to just meddle through and put big computing resources and a lot of patience. And that way we can push up to mass ratio 20, I would guess, roughly speaking. In fact, Sasha Husa and collaborators have already pushed up to mass ratio 18 with shortish simulations of about 5 orbits or so. But doing longer simulations at those high mass ratios, longer simulations there are important because post-Newtonian becomes less accurate, will require breakthroughs in the sense of more efficient and faster computing algorithms. I have no time scale for when those algorithms would arrive. From my own knowledge of what's going on in the field, I would not expect anything within the next 1 or 2 years.
Okay, if there are no more questions, let's thank Harald again and let's move on. Thanks a lot, Harald.